Hello everyone, thank you for attending my presentation. I hope you enjoyed the previous one on paper 928. This is paper 889 on the scalability of gelatin as a reservoir analog in hydraulic fracturing experiments. My name is Andreas Michael. A little bit of background on this project to start with. When I was a master's student at the University of Texas at Austin, I performed a series of experiments on highly concentrated gelatin blocks, which I had an aluminum tube simulating a horizontal well bore, and it had 3 holes in it, and I was trying to create 3 fractures from it, as we see from this setup that we see in this picture. And I believe I showed this picture in the previous presentation as well, and it was labeled with showing the 2 longitudinal fractures and 1 transverse fracture in between them in the middle. I did graduate in 2016 with my master's, and I wrote a master's thesis. This thesis became quite popular. It's, I believe, my most cited research publication, and that's a little bit surprising to me. Initially, I thought it's because of the extensive literature review, but it seems like there is other stuff, other novelties in it that made it popular. But I started a PhD afterwards, and eventually I transferred to LSU in 2018. I graduated with my PhD in 2020, and I was waiting for my work permit to arrive, which was delayed because of COVID. So I took this time to go back 5 years and convert this thesis to a journal article. And I published that in JNGSE, or the Journal of Natural Gas Science and Engineering, which at the time was, according to Google Scholar, the highest impact factor journal in the area of petroleum and natural gas. I think now it's second. In that study, I presented those series of experiments. However, when you are using a weird, let's say, or exotic reservoir analog like I did, questions will inevitably arise on the scalability. How well does it scale with the natural counterpart, which is reservoir rock? So that gave me that opened the door to a spin-off research on the properties of gelatin and its resemblance to reservoir rock in context of the scalability when it comes to its use as a reservoir analog in this kind of hydraulic fracturing experiments. Now, gelatin is 2 features that are very important. Is one that is transparent. So if you use colored fracturing fluid like I did, I used dyed glycerin, red dyed glycerin, you can see the fracture grow through it. And also it's brittle, which means that it behaves a lot like shale reservoirs or like reservoir rocks in general. It's not ductile, it doesn't deform when you apply stress to it, it actually cracks. A number of scientists in the past, they have published experimental work on hydraulic fracture experiments on gelatin samples, and that might be surprising to a few. It's not the most popular reservoir analog. I would say cement blocks or real rock is the most popular reservoir analog. However, gelatin is not a unique reservoir analog. It's not just me who used it. And I have here listed a lot of studies spanning, I don't know, 60, 70 years almost. One study that I would like to highlight here is Hubbard and Willis 1957, because that's a paper very important to hydraulic fractures. A paper that everyone knows, everyone claims that they have read, but not many of those have actually read. So yeah, he did some experiments on gelatin and he presented those in that paper. Despite those studies, I haven't seen a complete scaling analysis performed. The closest I have seen regarding scaling on gelatin is Kavanagh 2013, where she used gelatin to run experiments on magmatic intrusions or dikes with an I. And that's basically hydraulic fractures, tensile cracks with driven by molten rock. And in that study, she came up with some correlations for the basic mechanical properties of gelatin as a function of the gelatin concentration, the powder concentration, and I used those to evaluate those basic mechanical properties for my concentration range, which is from 7 to 8%. As we see here, that yields a Young modulus of 5.39 psi. Poisson ratio nearly 0.5. This is constant regardless of gelatin concentration, and is very close to the upper limit of 0.5, I guess. That will be the upper limit of the possible range that Poisson ratio can take for a solid material. Above that, it will violate the laws of thermodynamics. And the critical stress intensity factor, KIC, of 0.25 psi per square inch. Before finalizing on using gelatin, I considered other transparent reservoir analog material like urethane plastic, not to be confused with urethane rubber, and PMMA, or plexiglass, or it's basically bulletproof glass. And I finalized on using gelatin after seeing that the urethane plastic has a very high K1C, very high critical stress intensity factor. That makes it too ductile for our purposes. And PMMA has a very high tensile strength of about 10,000 psi, which makes it very hard to crack in the lab, considering the apparatus and equipment that we have. Gelatin satisfies the main criteria of being transparent, having low critical stress intensity factor, low tensile strength, and being cheap. Now, for the dimensional scaling analysis, I borrowed the theory of de Pader from a 1994 publication, where he used governing equations for simple planar hydraulic fracture propagation to come up with a number of dimensionless groups. Then these dimensionless groups were evaluated for the lab scale conditions and field scale conditions, and the two values were compared to come up with a lab to field ratio. And the closer this lab to field ratio is to 1, the more closer the scaling is to the ideal, which would be 1. I mean, in the real world, you cannot really get lab to field ratio equal to 1 unless you are really lucky. Generally speaking, if you are within 1 or maybe 2 orders of magnitude between the lab scale value and the field scale value of those dimensionless group, you are okay or acceptable. Now, these four dimensionless groups from the pattern that apply to these experiments are the treatment time, NT, which is given by the injection flow rate times the injection time period divided by the well-bore radius to the power of 3. Crack formation energy and gamma, which is equal to the square, the critical stress intensity factor raised to the power of 2 divided by 4 times G times the well-bore radius. G is very similar to the bulk modulus, but is slightly modified by the pattern and is what he called a fracture propagation modulus. And it still has units of dimensions of pressure, units of PSI. Elastic deformation, Ng, equals to G times the well-bore radius raised to the power of 3 divided by the injection flow rate times the effective viscosity for channel flow. Now, the effective viscosity for channel flow would be 12 times the apparent viscosity when it comes to cylinders. And I have here the power of 3 in red. That's because I made a typo on the paper, and I think I had power of 1. It's actually power of 3. And finally, the confining stress, which is given by the confining stress divided by G. Now, I compare the lab scale values of those dimensionless groups against field scale operations, and for those field scale operations, I used a typical hydraulic fracture treatment from the Barnett shale for slick water and crosslink gel. The difference is that the slick water has a lower fracturing fluid viscosity and allows a higher injection flow rate. And we see that my experiments do a better job scaling against the crosslink gel fracture treatment rather than the slick water. And that's mainly, almost exclusively in this case, in terms of the elastic rock deformation dimensionless group, which we see here being 6 times, 6 orders of magnitude apart from the field scale value. And when we use the crosslink gel fracture treatment, it's only 4. From this analysis, we can also, these results that I show here, the two tables, we can see that the critical stress intensity factor imposes a lower impact in the laboratory scale rather than the field scale, and the effective viscosity for channel flow imposes a higher impact in the laboratory conditions rather than the field scale conditions. So that implies that using a high fracturing fluid viscosity can reduce the impact of toughness and can compensate for the lower, inevitably lower laboratory injection flow rate. The treatment time is 2 orders of magnitude apart. Confining stress dimensionless group only 1, and then the crack formation energy is 5. In conclusion, I used highly concentrated gelatin mix conditions from my master's experiments to scale them against typical field operations from the Barnett shale and see how well the reservoir analog does against real operations. The scalability is more favorable when compared against crosslink gel field operations rather than slick water. And the lab scale experiments are predisposed towards accentuating toughness over viscous effects. And the only thing you can do about that is to increase the viscosity in the laboratory condition to improve scaling. Now, some of you, I understand that they are going to also be attending the ARMA conference, the American Rock Mechanics Association annual symposium this year. In that conference, I will be having a proposed set of laboratory conditions that can make gelatin blocks of higher concentration match those field scale operations at a higher degree. And with that, thank you very much.